All right, we're on page 2 of your notes, and we're going to look at some general reactions. Before we do that, we're going to just refresh your memory about which ones are the diatomic elements. The diatomic elements are the gang of 7 plus 1. The plus 1 is hydrogen. And the gang of 7 begins with the element nitrogen, goes across to oxygen, fluorine, and then ends up going down to chlorine, bromine, and iodine, making 7 total elements in the shape of 7. In addition to those diatomic elements, you're going to encounter some things. You might remember P4, you might remember S8. Those are various allotropes of phosphorus and sulfur. They're not necessarily the most common of those elements, but they are ones that you might encounter. So let's begin looking at synthesis. If you encounter 2 elements that are just reacting, like sodium and oxygen, you are going to encounter the oxygen in its diatomic form. So it's going to be the most common form of that particular element. In this case, since sodium is a metal joining with a nonmetal, you will make a lovely ionic compound, and that ionic compound will create a compound in which the normal or more common ions are being formed. So sodium is typically +1, oxygen is -2. So you'll make Na2O. On the other hand, you might encounter 2 nonmetals that are reacting. If you encounter 2 nonmetals that are reacting, you're actually going to be making a covalent molecule. And with covalent molecules, you don't always know what the oxidation state of the phosphorus is going to be. Oxygen will be a -2, but that doesn't necessitate what your compound is going to look like. In these cases, you do need to guess, and in a lot of your guessing, you're going to come up with something that makes sense or something that you've actually seen before. So let's say it's P2O5. Notice there is no charge on the compound, because again, it is a compound, it's not an ion. And there is a covalent sort of feeling because they're both nonmetals. The same is true if you encounter one of these binary compounds decomposing. So if you encountered Na2O and you were told that it was going to decompose, you're going to make the 2 elemental forms of it. There are a number of other synthesis and decomposition reactions that you may or may not be aware of. 2 oxides joining together, for instance, Na2O, so that's a metal oxide, joining with water, which is a hydrogen oxide, will create one individual ternary compound. Whatever you do, try to always list the element that is furthest to the left first. In this case, it's going to be sodium. After doing that, try to look at all of the other ions, or rather elements, and turn it into an ion. So we've got oxygens and we've got hydrogens. If I peruse my common ion sheet, I see that oxygens and hydrogens make a very nice ion of hydroxide. And so since they make a nice hydroxide, I'm going to join them together like so, making sodium hydroxide. Sometimes you're going to encounter ones, say for instance, your P2O5 joining with water. At this point you have a nonmetal oxide, so phosphorus with oxygen, and again you have a hydrogen oxide. Again, you're not going to know exactly how it's going to turn out. This is going to be a little bit of a guessing game. What you do know is whatever element is furthest to the left, so in this case it would be the hydrogen, that's going to get listed first. I recommend in situations like these, again, look at those elements. What do I have? I have oxygens and I have phosphorus. Join them together to make something that you might recognize. So a negative ion that includes phosphorus and oxygens is PO4. The charge of PO4 is -3, so I would need 3 hydrogens to join with it. And you're going to group them together to make these ternary compounds. Okay? The same is true if you go the other way. So let's say, for example, that you had lithium carbonate. So a ternary compound, oops, that should be a 3. You're going to break it down, you're going to create 2 oxides. So one of the oxides needs to be lithium with oxygen, the other one needs to be carbon with oxygen. So lithium with oxygen would be lithium 2, right, Li2O. Carbon with oxygen would be CO2. There are some others that are unusual. One of those includes metal chlorates, so KClO3. Potassium is the metal, ClO3 is the chlorate. When these decompose, you're going to take the metal and you're going to join it with the chloride ion. K is +1 and Cl is -1. You're also going to make oxygen as an element. Hydrogen peroxide is one that you really will have to just work on learning if you haven't learned it already. Hydrogen peroxide always decomposes to make some water and some oxygen gas. You then have some basic reactions that might be actually a little bit more comfortable. Single replacement is just going to switch out your metallic ion with another positive ion. So let's say, for example, you were putting some sodium metal into a solution, and that solution happened to have calcium sulfate. Since sodium is a metal and calcium is a metal, they're going to flip-flop. Sodium will now be the ion, Na+1, joining up with the sulfate ion. Calcium would now be the metal, not an ion, so a metal all by itself. If your element was in fact non-metallic, same idea, but it's going to look a little bit different. So let's say that you had Cl2 and you put it in a solution of sodium bromide. Cl is a nonmetal and bromide is the nonmetal. So sodium is going to actually stay the same. It's going to still be +1, but in this case the chlorine is going to switch with the bromine. Chlorine will turn into its ion form, so NaCl, and the Cl is acting as -1, so NaCl. Bromine is going to turn into its elemental form, and since bromine is part of that gang of 7, you're going to actually have Br2. You may instead be encountering some double replacement. Those are probably some of the easiest ones. You just flip-flop your ions. So let's say that you were encountering a little bit of copper nitrate solution, and you mixed it in with maybe some iron sulfate. Oops, let's do an iron 3 sulfate. So the hard thing is remembering what their charges are. When you're working with double replacement, whatever the charge was does not change. So if copper was +2 and iron is +3, they have to still be that when they come over to the other side. Iron is going to dump the sulfate ion and pick up the nitrate ion. So since iron was +3, we're going to need 3 -1 nitrates. Sulfate will get to join copper, since copper is now free and available, since it's left the nitrate ions. Again, copper was +2, has to stay +2. Sulfate is -2, it's got to be -2. So your double replacement reactions are going to look like that. Most commonly, if you're going to make a mistake, it's going to be the double replacement being confused with your acid carbonate or your acid sulfite. The reason for that is that your acid carbonate really does look like a double replacement. It starts out as 2 compounds. The problem is it's not going to act like your double replacement. when you encounter two compounds where one of them is an acid, and remember right now our definition of an acid means it's going to start out with hydrogen. If it's joining with a carbonate, that means that the carbonate ion is present in the other compound. As these join together, you will always make the water and the carbon dioxide. You're then going to take your other ions, so in this case the chlorine and the lithium, and you're going to join them together. Lithium goes first because she's the metal. Chloride comes next. Whatever the charge is of lithium, +1, it's still going to be +1. Chloride was -1, it's still going to be -1. That's the ionic compound that we know as a salt. All ionic compounds are known as a salt. So if you're going to confuse anything, you're most likely going to be checking double replacement versus your acid reactions. Those are the ones to look out for. I always recommend you try to find that acid carbonate reaction or acid sulfite reaction before you even think about double replacement. The last one is hydrogen combustion. And hydrogen combustion is any hydrocarbon. So it could be a hydrocarbon that's just got a whole bunch of hydrogens and carbons joining with oxygen, but it could also be a hydrocarbon that actually has hydrogens, carbons, and oxygens, so an alcohol like ethanol. Regardless, we're going to assume that every single one makes carbon dioxide and water. That is also assuming that they'll be stoichiometrically reacted, meaning that there's plenty of oxygen for the reaction to take place. You now have a series of examples that you might want to try and just go through and see how you do. Right now they're labeled. When you actually take the test, they're not going to be labeled. So practice them, ask questions about them, and also use some time to actually identify why they are the type of reaction that they are. If you have any questions, do feel free to ask Mr. Seiler or myself, as we of course will help you through. Good luck.